Hi everyone. So today we will examine we will see a brief introduction to the System Identification Toolbox, which is actually to me, is the most powerful tool for implementing, and also it's an opportunity to see how the theory that was examined in the lectures from, let's say, from 2 to at least 5 or 4.6, and they are automatically implemented. So is a way to see how these algorithms work, and they can be applied to real data, which is it represents, as we will see in the next module, it represents a way for, and I can add also, is a powerful way for obtaining a model of the system that needs to be controlled. So it represents one way for obtaining this kind of modeling. So let's start with this tutorial. Well, it's not really a tutorial. I have already provided in the website of my lectures the tutorial, which was delivered by Professor Leonard Jung, who is a well-known researcher working from many years in the field of system identification. He is one of the maximal experts on these topics, and by the way, is also the developer of this toolbox. So the toolbox, once you have opened the command windows in Matlab, just type the command ident. Ident is still working, and as you will see in as a warning, you can see that the command ident is obsolete and it may be removed in the next releases. So you can, but to me, ident is the shortcut. So it's very easy to remember, rather than the word system identification, but just remember this point. Okay, so once you have typed this command, you can see the main windows here, and it represents all your let's say desk where you can perform, or at least all the tasks or operations we saw in the theoretical lecture. And we will start from a basic tutorial example that it was presented in one of the last lectures. In particular, I think is the 4.6 or the 5, where the data of a hard dryer are already available. And so you normally start from, I would just explaining the most important feature of this tool. So you start normally with import data, and you can see that you can acquire data in the time domain, the frequency domain, from a data object, and an example that is the example that we will use today. But in the case normally, we have time domain data, and in fact, if you start from time domain data, you will see that a window will open, and normally you need to upload these variables as workspace variables. So it means that your variables need to be uploaded already in Matlab as workspace variables, and then you can see here that are time domain signals or data object, but our focus will be on time domain signals. So you can upload here these variables. Normally you can also specify a name, the starting time, a sample time. Okay, and normally once you have in here filled with the names of your variables, you just to push import, and then you upload the data. But now we don't have this data now in our space, and we will use the example. So just select from the menu example, and you can see here automatically we have as they should be available from the workspace U2 and Y2. They are from a dryer. The starting time is 0 and the sample time is 0.08 seconds. So you push the button import, and then you can see, then you can now this task is finished. So you can close this window, and then you have the dryer. You can see here that you have the data. This is just a sketch of your data. It's not really the trend of your data, but if you select here, for example, the time plot, you have now the window that shows how these data are, at least the power which is delivered to your to the heater of your hair dryer, and the temperature at the output. So normally, as you can recognize that this input is quite close to a pseudo-random binary sequence, which represent one of the most, as you remember, one of the most powerful inputs that can be used for identification. Because if you remember, a pseudo-random binary sequence has a very important characteristics of, and the most important is the persistency exciting feature. So it means that normally, depending on the period, you can estimate a model of arbitrary order. So it's one of, so it's very important point, this one. And also you can depict the data spectra, and so you can have the periodogram. So if you remember, the periodogram is like a very simple function. You can also select, instead of the periodogram, you can use a spectral analysis, which is something more, can be more have a better accuracy, and of course you can see here that depending on the length also of your sequence. Well, the idea is that depending, if you compare, for example, in periodogram, so you can well, in this case, just from the periodogram, you can see that the spectra is almost can resample the like white noise. So it means that it seems quite good for identification purpose. Then you can perform the pre-processing. When normally pre-processing, you can, for example, if you have multiple inputs, multiple outputs, so you can select a channel, specific channel, an experiment. You can have more experiments. So experiment means more data. So you can also select one experiment, a set of data, merge data, select also the range. You can remove means, the mean of your sequences, the trend. You can filter depending of a specific time frequency ranges, resample, make a transformation, or as we can see today, we can perform a quick start. And again, you can see here that in an automatic way, you have a series of operations. In particular, In blue, I enlarge this picture, these windows, and you can see here the data. These data are normally, as you can see here, they remove the trend, but so it means you remove the like a static value, and if there are some trends on your, like if you perform the time derivative of a signal, and you can see here that the only they are the trended and the data and the data where the mean value is removed. So there is no trend, but you can see here that there is a mean value which is different from 0. So now you have the sequences that are 0 mean, and it's very important because this filter improves the numerical reliability of your algorithm, and then you can separate your data in two sets. And in particular, you can, in red, you have your estimation. In fact, you have the last letter of your original sequences. Your original data is with these, the trended or removed. So filtered, and then you have two sets, the set that you can use for the estimation and that data that you can use for the validation. So if you remember, this represents an important way for, as we saw in one of the last lectures, so is the normal cross validation of your models. Then once we see that in the working data, so these windows represent the data that are used for the estimation. Is why they are using the letter E. And but in the validation data, you can see here that they are normally they are the data, the second part of the data that are used, that are indicated with the letter V. Normally, you can move by clicking the left button of your mouse and hold the button, you move, you drag your data and you put here. But if you select pre-process quick start in an automatic way, your starting data are filtered and partitioned into two sets. Then we can perform the estimate. Well, again, you can see here we have different types of model. As you can easily recognize, we have the transfer function models, state space, process, polynomial models, nonlinear. Nonlinear is something that we didn't consider, but because they have a special form of models, they are normally called as Hammerstein-Wiener, because they can have a dynamic linear part and a static nonlinear part. It's something that can be considered. And then if you remember, if you recognize, we can estimate the spectral models. If you remember from the correlation analysis, you can start from the correlation models that they are obtained quite quickly with the correlations functions, and then they are transformed with the fast Fourier transform. You can obtain a spectral model. You can refine an existing model in order to improve some characteristics, and then you can select a quick start. We will use this way. So a quick start, if you select this option, it takes some time, and so in an automatic way, you can see here just wait and okay. So you can see here in an automatic way you obtain different models. Well, the first two models are I remove these options, and then we can see it. So we have the impulse, so is the correlation model, the spectral frequency model. Then we have a Rx model, so is the simplest one that we can obtain. As if you remember, it means the Rx is the model that is modeling the deterministic part of your system as a transfer function where the numerator is b and the denominator is a, so two polynomials, and the stochastic part of the noise is filtered by a filter where the denominator is a, so they are sharing the same polynomials at the denominator, if you remember, the Rx. And then we have this is important because is a state space model, and in particular you can see here that is the order is 3, so it's determined in an automatic way in order to, if you remember, the automatic selection of the model structure. So we will see some examples. For example, if we for example we select the transfer function model, just to show you. Now we'll just wait for. It's taking some time. Let's see if something. Okay. So you can, of course, you can select a model structure at discrete time. Normally, you can decide the number of poles, the number of 0. So depending on the order, in the estimation options, you have a number of options that you can select, or you can use a polynomial model. So is another. In this case, if we have, if you, for example, you see, if you select a polynomial model, so instead of a transfer function model, so where only the deterministic part is modeled, you can, if you select the polynomial model, you can see here from the structure that you can select the 4 classes of models we revised, we saw in the theory. So Rx, Rmax, output error, Boxa-Jenkins. Let's limit our investigation for now at the Rx model. So we are selecting the Rx, so it means that it's using, for example, a least square approach, or you could also use an instrumental variable. But if you remember, the instrumental variable is something that tries to copy the least square approach, but in some cases it leads to less accurate solutions. And you can, for example, order. If you click here, order selection, you can see here that it tries to estimate all the models. So it means that it's trying to combine all the possible values between 1 and 10, 1 and 10, 1 and 10 for N, A, and B, and C. And if you click estimate now, it takes times, and you can recognize just I selected this option because in fact you can see here that we found if you remember the estimation criteria. That are these criteria that, in particular, the minimum description length or the Akaike information criterion, in fact, is saying that according to the green, to meet the minimum description length, which is green, and if you click to green, you have that the select it's suggesting a number of delays for the polynomial denominator is 3, the number of delays for the numerator is 4, and the number of delays between the input and output is 2. And according to the blue one, as you can see here, that with respect to the green one, is adding 2 more poles, and the green one is the best choice. So which it means that is best fit. So it tries to reduce the loss function. And but if you notice, is the choice of the model is the normal is the green one, because as you notice from the decreasing of this const function, you can see here that there is a very small change in the misfit if you move from the green one, which is 0.19511, and by increasing the order of, so if you add two more parameters, you pass from 0.19 to 0.19 but 26. And if you consider 15 parameters, it's really decreasing, but not so with a big change. So you can, I think, for the model that we need to we can consider, you can select safely the order 3, 4, 2. But remember that we have an NK. So if you remember, NK is the delay between the input and the output. Let's see if this suggestion of NK equal 2 is really. So this is the, we can close this one. So we can, for example, deselect these models, and let's see, for example, the model output. And the transient response, if we can see something. See if, okay, now we have, this is the model output, and the transient. Well, in fact, you can see here that, in fact, if you notice the step response, you have, in fact, there is a delay between 0 when, so it means when the step starts at 0, and you see here that for the first almost for the first 2 samples, so if you remember, the sampling time is 0.08, so the output, let's say, is moving only after 2 samples. So in fact, this is something that is suggested in your, if just a second, okay, is something that we saw when, in fact, we estimate, if you remember, the number of delays in your model. And we have also thought this is something that is confirmed by the impulse response. And if you consider the spectral analysis, we can see, for example, selecting the frequency response. So you can see here that when you compare the frequency response, which is estimated from the correlation analysis, with, for example, you select your estimated model, you can see that, of course, the phase is not really represented apart from the state-space model. In fact, the space model is quite different, but you can see here that the selection, the RX estimated RX model is following quite nicely the frequency response. And you can see also, if you select the impulse response and you select the model output, we can see here that the model output is quite close to the, for example, the impulse response provides a best fit of 89%, and the estimated RX model is 89.44. So it means that the accuracy of the estimation is quite good. And if you select, also the state-space model is describing quite good the output of your system. So all your estimated models are quite accurate, but note that you are depicting. So you are showing the simulation. So it means, if you remember the difference between one-step ahead prediction and estimation, so you can change from the simulation. So you change the prediction horizon in one, and then you select one-step ahead prediction. So if you notice, the one-step ahead prediction is really even better than, of course, the simulation. But in order to understand that your model is really good, normally you select the simulation, because if you remember from one of our lectures, the simulation is something that is comparing only the deterministic part of your model, and if the model is really good, it means that it provides a very good simulation. And then, but in order to understand if your model is good, normally you are, if you remember, you select the residual. And if you remember something, that it was something that, for example, was analyzed in one of our lectures. And if you remember, when a model is optimal, so it means it provides the optimal estimation, the correlation, the autocorrelation and the cross correlation of the residual should indicate that these residuals are white. But of course, you can deselect, well, the impulse response can be removed. And also you can notice that also the state-space model is not really good, and so the model residual can be the model residual is something that is saying, well, the residual is almost white, not perfectly, but let's see which kind of model. If you click on the model, you can see here that in fact you notice that is estimating a model of with the order 4, 4, 3. So it means that 3 is not really describing, in my opinion, the real delay of your between the input and the output. So let's come back to the manual. So let's say not the automatic, but the manual, and let's select the polynomial models, and then again, just to see, let's see the order selection, and then to estimate. So let's try to see these three models that are suggested by the selection, the model order selection criteria. So let's try to select. If you click and then you push the right button, let's select 3, 4, 2 and insert. And then you will see that your model is included here in your, let's say, matrix or your possible models. And then let's select the blue one and then the green one in order to understand the comparison. So we can compare, or you can also move these two models, in order to, let's say, rearrange our models so we can divide. So we have the correlation, so the impulse, the correlation analysis, spectral analysis, Rx estimated in an automatic way, Rx models, three models of the different order, but so the order, the Rx model obtained in an automatic way, the three models that we selected on the basis of the suggestion given by the selection order criteria, and then the state space model of order 3. And let's compare these three models. So the model output, we can see here that, let's compare these three models and then the model that was selected in an automatic way. Well, in fact, our three models provides the best estimation with respect to the model obtained in an automatic way. And let's check the residuals. Let's see what's happening. Well, in fact, if we see these three models, you can notice that by considering the you can see here that the red model is the model obtained in an automatic way. Is a cross correlation. You can see here that this function is violating the upper threshold. So it means that if you remember that the delay between the input-output is not correctly modeled, so it means that the n key equal to 3 is wrong. So let's remove this model, and we can see that when you consider the whiteness, only let's try to reduce this picture. So the model that is really, well, apart from a small, but the only model that is providing a white noise seems to be the model 692. But again, let's consider all the three models. When we, for example, let's go and see the zero and poles, we can notice that For example, if we and option unit, okay, the unit circle, we can try to, okay, we have some external zeros, and for example, let's see, okay, okay, let's see if, okay, so we have for the case of the model order, we can see that there are 2 poles here, 1 0 here, but it seems that these 2 pole and 0 are quite close to be cancelled. So perhaps the order used by this model is quite high. This one, in fact, is 4 4 3, so maybe is using perhaps too many parameters. But if we consider the 3 4, we can see here that apart from a 0, which is outside of the unit circle, but it seems that the poles are not cancelled, so it means that the number or the order can be true. And if we compare from adding a number 2 more parameters, if we add 2 more parameters, it seems that there's a cancellation in the, if you notice here, because there are 1 0 and 1 pole, and then here, so it means that perhaps these models and also this one is the order is perhaps is too high, so it means that perhaps we can remove this, we can not consider these 2 models, and then perhaps the best one is this one. Let's try to analyze this model here. So the model, we remember that, well, of course, is 85.51 compared with the, so the Rx seems a little bit better. And in terms of 0 poles, we can say that the model is, it seems that the order is appropriate. So it means that also this one can be good. So finally, we can say that, just to summarize, in order to have a view. So you can see here that you can estimate different models. So correlation, spectral data are used in order to understand if the selection of your delays in between the input and output is correct. There is an automatic model selected in an automatic way that perhaps it uses too many parameters. And on the other hand, we estimated 3 models in order to obtain, or at least to satisfy, for example, the minimum description length, a Kaike information criterion, and the best fit. And definitely, perhaps these 2 models are using too many parameters. Well, the state space model is of order 3, maybe is quite can be interesting. Let's say, just before closing, you can perform an a preliminary estimation of your state space model. So if you select state space model, and then you discrete time, let's see if we can perform a subspace. Okay, let's see if we can. Okay, so you have, now you can see that using, you have the automatic selection according to the, let's say, a criterion which is suggesting the order tree. So, well, in fact, the system is selecting the order tree, which is the one in red, and it seems that according to this criterion is the best. So the model of order tree, so tree means with 3 poles, can be considered as the best model. So also for the state space models, you have the you have this option of estimating the your orders. So in order, once you have obtained your models, in order to put them in the workspace and then to use them for control purpose, for example, if you select this one, you drag and put into workspace, and if you check in your workspace, now you find these ARX 342, and this is the model that can be used for example, of course, only the deterministic part can be used for the control purposes, or you can also export this model, again, to workspace. And then if you go here, you have N4S3, and you can extract these matrices. So when we will see, for example, the design of your model, it's very simple to extract the matrices, because if you write N4, so the name, you have the matrix A, and in this way you can extract very easily the parameters of your model. So A, B, C, D. So if you can see here, it seems that is a poorly dynamic model, because D is 0, and this can be obtained as a state space model. So we will see how to use it for the design of a controller. So I think we examined all the possible issues for a model identification, and well, once we will go to the design of a controller, well, we will use the System Identification Toolbox for estimating the model, and then with this model we can design our controller. Okay, thank you for your attention, and that's all. Thank you again.